We go now to 2.2.3, the numerical derivative on a calculator. A few new vocabulary words here. We have the symmetric difference quotient, we have the numerical derivative of f at a, and we have the numerical derivative of f, but no new theorems or rules. So let's begin this way. For small values of h, the difference quotient that we know and are used to, f of a plus h minus f of a all over h, is often a pretty good numerical approximation of f prime of a. So what we're saying here is this is approximately f prime at a. But suggested by the figure we're going to draw on the next page, the same value of h, and remember h is just a very small number, is going to yield a better approximation of f prime of a if we use something called the symmetric difference quotient. This looks slightly different than the difference quotient that we're used to. This is f of a plus h minus f of a minus h over 2h to compute the slope between two nearly identical points on opposite sides of A. In fact, this approximation, which calculators can easily compute, and we're going to say here graphing calculators, it's close enough to be used as a substitute for the derivative at a point in almost all applications. So the symmetric difference quotient is going to be an even better approximation for f prime of a. Let's figure out how to compute it. So I've got a graph here, and we're going to go over to Desmos and see the actual graph pretty soon, but let's take a look at what it might mean right now. So first of all, the blue curve, let's say that's y equals f of x, so that we are all on the same page of the function. And then I've got a point in the function. You can see the black point here, and this is x equals, let's call it a. And then h spaces away from a, I have put another point way out here, and this is h away. And the green line secant between those points is drawn in. And that's the line that would be generally used for our difference quotient to get that secant slope. And if you compare that line to the red line is the actual tangent line at x equals a. Let's say that. This is the tangent line at x equals a. You can see that there is quite a bit of a difference between the slopes of those two lines. The secant line using the difference quotient and the tangent line, maybe not a huge difference, but a bit of a difference still. Now, the symmetric difference quotient, here's how we would use this one. I've also placed a point on F that is h spaces to the left of A, and now we've drawn a secant line through each of those points. So let's calculate what that slope would be. So here we have the x value x minus h, and here we have the x value x plus h. So the slope between those 2 points would be f of x plus h minus f of x minus h. So there's the y value minus the y value over the x value of the point to the right, which is x plus h, minus the x value to the point on the left, which is x minus h. And this would simplify then to f of x plus h minus f of x minus h all over. Now, x minus x makes 0, h minus a negative h is 2h, and there is what we call the symmetric difference quotient. Now, let's take a look at that line compared with the actual tangent line. You can see that the line using the symmetric difference quotient is much closer to being parallel to the line, the red one, the tangent line at x equals a. And because it's much closer to being parallel to that line, its slope is a much better approximation for the derivative at our point in question. And so let's come over to Desmos, and here's a picture of, or here's the graph of the picture that was in the notes. And I've got h right now as a small number, about 2.5. That's the space between our point and the point to the right and the point to the left. And we can get closer and closer. We can bring h down. And even though both the difference quotient slope line and the symmetric difference quotient slope line both eventually approach the actual tangent line, the symmetric difference quotient is much closer to being parallel right now and is therefore a much better approximation of that derivative. So let's head back to the notes and continue forward. Here we have the definition. The numerical derivative of f at a, which we're going to denote in deriv of f of x comma a, is this number, f of a plus 0.001 minus f of a minus 0.001, where this number is h and this number is h. Remember, h is just a very small number, and here is 2h. And then the numerical derivative of f, notice this is the general version of the derivative, not at a point. We replace the a with an x. So we have f of x plus 0.001 minus f of x minus 0.001 all over 0.002. Your TI-84s and other similar Texas Instruments calculators use this notation in deriv, and they will calculate this right here, this version, f of x comma a in classic mode. But most of you probably don't have your TI-84 set in classic mode. They're probably in math print mode, and we use this notation, ddx of f of x, and then a bar to evaluate x at some point a. Here's an example. Let's compute the numerical derivative with this setup. If f of x is equal to x cubed, let's use the numerical derivative to approximate f prime of 2, both by hand and using a graphing calculator. So the numerical derivative would look something like this. F prime of 2 is approximately equal to f of 2 plus 0.001 minus f of 2 minus 0.001 all over 2 times that, so 0.002. All right, let's use our graphing calculator to do this. So here's our calculator, and let's go back to the home screen. And we want to use this function, the cubic function. So let's set up a fraction, and we're going to plug in 2 plus 0.001 there. So we're going to go parenthesis 2 plus 0.001 and cube it. And then we're going to go minus 2 minus 0.001 and cube it. And then this is going to be over 0.002. And let's see what we get here. 12.000001. So it's at the 6th decimal place that we get a 1. Now, let's use the built-in numerical derivative function. So we hit the math button. We notice here in option 8, we have in deriv. That stands for numerical derivative. Let's hit 8. And you can see my calculator is in math print mode. And so we've got this Leibniz notation. We want ddx, so we hit the variable button of our function is x to the power of 3. And we'd like to evaluate the numerical derivative at x equals 2. So this is f prime of 2. And we hit enter, and hey, they're the same thing. So the numerical derivative of x cubed is calculated this way. And what we just did in the first line is the longhand version. So we're going to note here that ddx of x cubed at x equals 2, both of these get the same answer, 12.1234. Oops, there's one more, 5, and then it's the 6th decimal place, 12.000001. And this is an approximation of the numerical derivative at x equals 2. We learned in a previous section that if f of x is equal to x cubed, f prime of x is 3x squared. We could find that derivative with the limit definition. So we know that f prime of 2's actual answer is 3 times 2 squared, which is 12. And so you can see the numerical derivative is such a good approximation. It's the tens, hundreds, thousands, 10,000s, 100,000s. It's the millionths place where we're finally off by a little bit. So a super good approximation using inderiv. Here's another. We want to compute inderiv for the absolute value of x comma 0, which is the numerical derivative of the absolute value of x at x equals 0 by hand and using the graphing calculator. What do we notice? Now, I've put this one in here for a reason. We know that the absolute value function of x is not differentiable at x equals 0. So what happens if we use inderiv? Let's start with the calculator. So we're going to go alpha. Actually, we're going to hit math and go down to inderiv and ddx, the derivative with respect to x, math. And we want the absolute value function. So over to number and then option 1 of x. And we want to calculate this derivative at x equals 0. Let's hit enter. And this says the derivative is 0. And we know for a fact this function is not differentiable there. So what happens if we try to calculate it by hand? Well, we would have the absolute value of 0 plus 0.000, or actually there's 2 zeros, 0, 1, minus the absolute value of 0 minus 0.001, and then this is over 0.002. Well, let's see. We have 0.001 minus the absolute value of negative 0.001, so that becomes 0, and this is over 0.002, which is 0, and so even by hand, we get a number 0, and we know that can't possibly be the derivative at x equals 0 because f is not differentiable there. So inderiv is not exact. So this is going to give us an answer sometimes when we know that the function is not differentiable. It is an approximation. All right, so it's just important to keep that in mind. Sometimes inderiv can kind of lie to us. Here's the last example of this section. Let's let f of x be natural log of x and use inderiv in our calculator to graph y equals f prime. And can we guess from that graph what function f prime of x is analyzing in its graph? Well, this is interesting because I've just explained that our calculator does numerical derivatives, but it can't exactly find an algebraic derivative because it doesn't have a computer algebra system. So the TI-84 has no CAS. It doesn't have a computer algebra system, so it can't explicitly find f prime of x. But what we can do is what I call kind of tricking the calculator into graphing f prime. So it can graph y equals f prime of x. And let's see how that happens. So let's clear the screen. Let's go to our y equals screen and clear both of these out. And let's go up to y1. And we're going to, instead of typing in a function to y1, we're going to hit math and option 8 for inderiv. So our y1 is going to be the derivative of a function. And we want that function to be, in this case, for example, natural log of x. And rather than graphing the derivative at a particular point, which would obviously just be a horizontal line because the derivative would be a real number, we're going to have x is equal to, I'm just going to hit x again. So what this will do is kind of ask your calculator to plot the numerical derivative of the natural log of x at every x in the view screen. And let's go zoom decimal here. Sometimes this takes our calculator quite a bit more time than normal because it's doing a lot of work here to graph this function. And that actually, now that I see it, that looks like a very kind of familiar function. Let's do trace and see if we can find some numbers on here. So 0.4 comma 2.5, all right, 1/2 comma 2. Okay, that's starting to sound familiar. What's the value at 1? Oh, 1 comma 1. What about at 1.5? 2/3. What about at 2? Oh, at 2, the value of the function is 1/2. I know what function that is, and you probably do too at this point. This function appears like 1 over x. Can I guess what f prime is? F prime is 1 over x. And we're going to learn in a future section exactly how to prove that that's the case. The derivative of natural log of x is 1 over x algebraically. But for right now, it looks like the numerical derivative gives us a pretty good idea that that is the case. And that ends this video for us.